reaching every learner with compassion, moving everything with passion, driving everyone with dedication. This is Idukat Balogan by Enhance.
Good day, our dear learners from Catbalogan City Division. I am teacher Elena and Beduya. Welcome for today's lesson in General Mathematics for Grade 11 Senior High School. The topic that we are going to tackle today is about exponential functions. After this episode, I expect that you should be able to identify exponential function, exponential equation, and exponential inequality. Second is find the solution set for exponential equations and inequalities. And last, represent an exponential function through its table of values, graph, and equation. After a short break, we will start our discussion. Please be ready with your modules, paper and pen for our activities.
The phrase exponential growth is familiar to most people. And yet, human intuition has a hard time really recognizing what it means sometimes. We can anchor on a sequence of small-seeming numbers and then become surprised when suddenly those numbers look big, even if the overall trend follows an exponential perfectly consistently. This right here is the data for the recorded cases of COVID-19, aka the coronavirus, at least at the time that I'm writing this. Never one to waste an opportunity for a math lesson, I thought this might be a good time for all of us to go back to the basics on what exponential growth really is, where it comes from, what it implies, and maybe most pressingly, how to know when it's coming to an end. Exponential growth means that as you go from one day to the next, it involves multiplying by some constant. In our data, the number of cases in each day tends to be a multiple of about 1.15 to 1.25 of the number of cases the previous day. Now, viruses are a textbook example of this kind of growth, because what causes new cases are the existing cases. So if the number of cases on a given day is n, and we say that each individual with the virus is exposed to, on average, e people on a given day, and each one of those exposures has a probability p of becoming a new infection, then the number of new cases on a given day is e times p times n. And the fact that n itself is a factor in its own change is what really makes things go fast, because if n gets big, it means the rate of growth itself is getting big. One way to think about this is that as you add the new cases to get the next day's count, you can factor out the n. So it's just the same as multiplying by some constant that's bigger than 1. This is sometimes easier to see if we put the y-axis of our graph on a logarithmic scale, which means that each step of a fixed distance corresponds to multiplying by a certain factor. In this case, each step is another power of 10. On this scale, exponential growth should look like a straight line. Looking at our data, it seems like it took 20 days to go from 100 to 1,000, and 13 days to go from that to 10,000. And if you do a simple linear regression to find the best fit line, you can look at the slope of that line to draw a conclusion like, we tend to multiply by 10 every 16 days, on average. This regression also lets us be a little more quantitative about exactly how close the exponential fit really is, and to use the technical statistical jargon here, the answer is that it's really freaking close. But it can be hard to digest exactly what that means if true. When you see one country with, say, 6,000 cases and another with 60, it's easy to think that the second is doing 100 times better, and hence fine. But if you're actually in a situation where numbers multiply by 10 every 16 days, another way to view the same fact is that the second country is about a month behind the first. Now this is, of course, rather worrying if you draw out the line. I'm recording this on March 6th, and if the present trend continues, it would mean hitting 1 million cases in 30 days, hitting 10 million in 47 days, 100 million in 64 days, and 1 billion in 81 days. Needless to say, though, you can't just draw out a line like this forever. It clearly has to start slowing down at some point. But the crucial question is when? Is it like the SARS outbreak of 2002, which capped out around 8,000 cases? Or the Spanish flu of 1918, which ultimately infected about 27% of the world's population? In general, with no context, just drawing a line through your data is not a great way to make predictions. But remember, there's an actual reason to expect an exponential here. If the number of new cases each day is proportional to the number of existing cases, it necessarily means each day you multiply by some constant. So moving forward d days is the same as multiplying by that constant d times. The only way that stops is if either the number e or p goes down. It's inevitable that this will eventually happen. Even in the most perfectly pernicious model for a virus, which would be where every day each person with the infection is exposed to a random subset of the world's population, at some point most of the people they're exposed to would already be sick, and so they couldn't become new cases. In our equation, that would mean that the probability of an exposure becoming a new infection would have to include some kind of factor to account for the probability that someone you're exposed to is already infected. For a random shuffling model like this, that could mean including a factor like 1 minus the proportion of people in the world who are already infected. Including that factor, and then solving for how n grows, you get what's known in the business as a logistic curve, which is essentially indistinguishable from an exponential at the beginning, but ultimately it levels out once you're approaching the total population size, which is what you would expect. True exponentials essentially never exist in the real world. Every one of them is really the start of a logistic curve. Now this point right here, where that logistic goes from curving upward to instead curving downward, is known as the inflection point. There, the number of new cases each day, represented by the slope of this curve, stops increasing and instead stays roughly constant before it starts decreasing. So one number that people often follow with epidemics is the growth factor, which is defined as the ratio between the number of new cases one day and the number of new cases the previous day. So just to be clear, if you were looking at all of the totals from one day to the next, then tracking the changes between those totals, the growth factor is a ratio between two successive changes. While you're on the exponential part, this factor stays consistently above 1, whereas as soon as your growth factor looks closer to 1, it's a sign that you've hit the inflection. This can make for another counterintuitive fact while following the data. Think about what it would feel like for the number of new cases one day to be about 15% more than the number of new cases the previous day. And contrast that with what it would feel like for it to be about the same. Just looking at the totals they result in, they don't really feel that different. But if the growth factor is 1, it could mean you're at the inflection point of a logistic, which would mean the total number of cases is going to max out at about 2 times wherever you are now. But a growth factor bigger than 1, subtle though that might seem, means you're on the exponential part, which could imply there are orders of magnitude of growth still waiting ahead of you. Now, while it's true that in the worst case situation the saturation point is around the total population, it's of course not at all true that people with the virus are randomly shuffled around the world's population like this. People are clustered in local communities. However, if you run simulations where there's even a little bit of travel between clusters like this, the growth is actually not that much different. What you end up with is a kind of fractal pattern, where communities themselves function like individuals. Each one has some exposure to others, with some probability of spreading the infection, so the same underlying and exponential inducing laws apply. Fortunately, saturating the whole population is not the only thing that can cause the two factors we care about to go down. The amount of exposure can also go down when people stop gathering and traveling, and the infection rate can go down when people just wash their hands more. The other thing that's counterintuitive about exponential growth, this time in a more optimistic sense, is just how sensitive it is to this constant. For example, if it's 15%, like it is as I'm recording this, and we're at 21,000 cases now, that would mean that 61 days from now you hit over 100 million. But if through a bit less exposure and infection, that rate drops down to 5%, it doesn't mean the projection also drops down by a factor of 3, it actually drops down to around 400,000. So if people are sufficiently worried, then there's a lot less to worry about. But if no one is worried, that's when you should worry.
This is one of the many examples of exponential growth. The more infected people we have in the disease outbreak, the more people will be infected and the more cases will rise. So stay safe, stay at home. To have a deeper understanding of today's lessons, let us begin our lesson with this activity. The activity is entitled, Where Do They Belong? From the expressions given, you are going to classify whether it is an exponential function, equation, inequality, or does not belong to any of these three. I will give you 1 minute to answer. Let us go back to the activity, then check your answer if you answered it correctly. Did you get it right? Very good. Now, let us discuss the difference between exponential function, exponential equation, and exponential inequality. In your previous grade level, you were asked to differentiate between equation and inequality. Maybe one of your answers could be the inequality sign for equations and inequality sign for inequalities. How about functions? An exponential function is a function involving exponential expressions showing a relationship between the independent variable x and dependent variable y, or f of x. An exponential equation is an equation involving exponential expression that can be solved for all x values satisfying the equation. An exponential inequality is an inequality involving exponential expression that can be solved for all x values satisfying the inequality. Why do you think these three under the column none of this? Excellent observation. They do not satisfy the definition of exponential function. Always remember, an exponential function with base b is a function of the form f of x equals b raised to x or y is equals b raised to x, where b is greater than 0 but b should not be equal to 1. To be more specific, the base must be greater than 0 but not equal to 1, and its exponent is a variable. Let us have a quick review on exponential functions, equations, and inequalities. An exponential function with base b is a function in the form of f of x equals b raised to x or y equals b raised to x, where b is greater than 0 but b should not be equal to 1. An exponential function is a function involving exponential expression showing a relationship between the independent variable x and the dependent variable y or f of x. An exponential equation is an equation involving exponential expression that can be solved for all x values satisfying the equation. An exponential inequality is an inequality involving exponential expression that can be solved for all x values satisfying the inequality. Just like other functions, there are also ways in finding the solution set for exponential equations and inequalities. Let us start by recalling the laws of exponents. Multiplication rule. A raised to m times a raised to n is equal to a raised to m plus n. Power of a power rule. A raised to m raised to n is equal to a raised to m times n. Power of a product rule. A times b raised to m is equal to a raised to m times n. Division rule. A raised to m divided by b raised to n is equal to a raised to m minus n. Power of a quotient rule. A divided by b raised to m equals a raised to m divided by b raised to m. Zero exponent. A raised to 0 is equal to 1. That is, any number raised to 0, the answer is 1. Negative exponent. A raised to negative m is equal to 1 over a raised to m. If you raise a base to a negative exponent, just get its reciprocal. Fractional exponent. A raised to m over n is equal to the nth root of a raised to m. In the fractional exponent, the numerator becomes the exponent of the radicand and the denominator is its index. Now that you have recalled the laws of exponents, let us do the next activity. Finding the missing x.
Aww.
You are going to solve for the unknown variable in the given exponential function. For letter A, 8 raised to 2 minus x is equal to 2, and for letter B, 4 raised to 3x equals 8 raised to x minus 1. I will give you 1 minute to answer. How did you answer the activity? Please check if you have done it correctly. For letter A, 8 raised to 2 minus x equals 2. Your first target is to make the bases equal. You can rewrite 8 as 2 raised to 3. Therefore, it will become 2 raised to 3 raised to 2 minus x equals 2 raised to 1. Since they have the same base, you can now equate its exponent. This is now solving linear equations. 3 times the quantity 2 minus x is equal to 1. By distributive property, 6 minus 3x is 1. Isolate the variable on the left side and the constant terms on the right side by applying addition property will give you negative 3x equals negative 5. To eliminate the coefficient of the variable, multiply the whole equation by its reciprocal, that is, negative 3. Then cancel negative 3 because it's now equal to 1. Therefore, x is equal to 5/3. You may check if your answer is correct by substituting the values of x to the equation. For letter B, 4 raised to 3x equals 8 raised to x minus 1. 4 is equal to 2 raised to 2 and 8 is equal to 2 raised to 3. Rewriting the bases, the equation becomes 2 raised to 2 raised to 3x equals 2 raised to 3 raised to x minus 1. Equate the exponents since they have the same base. Applying distributive property, it becomes 6x equals 3x minus 3. Then combine like terms, so 6x minus 3x becomes 3x equals 3. Divide both sides by 3, that is x equals to 1. I hope you understood on solving exponential equations. Always remember, the first step, make the bases equal and equate the exponents, and the rest will follow. Let us now go to our next lesson, solving exponential inequalities. However, we need to recall first the properties of inequality and the rules in solving inequalities. Properties of inequalities. If b is greater than 1, then the exponential function y equals b raised to x is increasing for all x. This means that b raised to x is less than b raised to y, if and only if x is less than y. If the base is greater than 1, the direction of the inequality is retained. If b is greater than 0 but less than 1, then the exponential function y is equal to b raised to x is decreasing for all x. This means that b raised to x is greater than b raised to y if and only if x is less than y. If the base is less than 1, the direction of the inequality is reversed. For the rules in solving inequalities, if the same real number is added to or subtracted from both sides of the inequality, the sense of the inequality is not changed. If both sides of the inequality are multiplied by or divided by the same positive real number, the sense of the inequality is not changed. If both sides of the inequality are multiplied or divided by the same negative real number, the sense of the inequality is changed. Let us again have an activity on finding the x, but this time it's for exponential inequalities. I will give you 1 minute to answer. How did you answer the activity? Please check if you've done it correctly. Let us answer letter A. From the second property of inequality, if b is greater than 0 but less than 1, the direction of the inequality is reversed. So, from less than sign, change it to greater than sign. Just like solving exponential equations, the next step is to make the bases equal. 1 over 8 is also equal to 1 over 2 raised to 3. Equating the exponents, x is greater than 3, therefore, the solution set are 3 to positive infinity. Parentheses is used in the set notation since 3 is not included in the solution set. For letter B, since the base is greater than 1, the inequality symbol is retained, meaning we are not going to change the inequality sign. We can rewrite 27 as 3 raised to 3 to make the bases equal. Equating the exponents will give you x is greater than or equal to 1. Therefore, the solution set are 1 to positive infinity. Take note, bracket is used since 2 is included in the solution. Exponential functions can be represented as equations, and it can also be represented by graphs and table of values. Our next lesson is representing exponential functions through equations, graphs, and table of values. Let us have this example. Sketch the graph of f of x equals 2 raised to x. The first thing to do is to construct a table of values by assigning values of x, then solve for y. So if you assign negative 3 for x, then y is equal to 1/8. Negative 2, 1/4. Negative 1, 1/2. 0, 1, 1, 2, 2, 4, 3, 8. From this table of values, plot the points in the Cartesian plane. Then, connect the points on smooth curve. This is now the graph of 2 raised to x. Properties of the graph of exponential functions. First, the domain is the set of all real numbers. Next, the range is the set of all positive real numbers. It is a one-to-one function. It satisfies the horizontal line test. The y-intercept is equal to 1. There is no x-intercept. The horizontal asymptote is the line equals 0 or the x-axis. There is no vertical asymptote. The function is increasing if b is greater than 1 and decreasing if b is less than 1. If we go back to the graph of 2 raised to x, so the domain is the set of all real numbers since the graph has positive and negative x values. The range is the set of all positive numbers since it has only the positive y-axis. The y-intercept is 1 because the graph intersects at y-axis at 1. The horizontal asymptote is at y equals 0 or at the x-axis. The graph is increasing since y is greater than 0. That ends our lesson for today. Please remember the important points in exponential functions. An exponential function with base b is a function of the form of f of x equals b raised to x or y equals b raised to x, where b is greater than 0 but b is not equal to 1. An exponential function is a function involving exponential expression showing a relationship between the independent variable x and the dependent variable y or f of x. An exponential equation is an equation involving exponential expression that can be solved for all x values satisfying the equation. An exponential inequality is an inequality involving exponential expression that can be solved for all x values satisfying the inequality. In solving exponential equations and inequalities, you should have the same base, then apply the steps in solving equations and inequalities. Properties of the graph of exponential functions. The domain is the set of all real numbers. The range is the set of all positive real numbers. It is a one-to-one function. It satisfies the horizontal line test, and the y-intercept is 1. There is no x-intercept. The horizontal asymptote is the line y equals 0 or the x-axis. There is no vertical asymptote. The function is increasing if b is greater than 1 and decreasing if b is greater than 0 but less than 1. Now that we are done with our lesson, I will give you a short quiz to check if you understood the topics today. Let us check if you answered it correctly. How many correct answers did you get? If you got perfect, congratulations! Please answer the activities in your modules for general mathematics to understand the topics more. Let me end our session by having this quote from Christian D. Larson, and I quote, "Believe in yourself and all that you are. Know that there is something inside you that is greater than any obstacle." And that's all for today's episode in General Mathematics. I hope you have learned something from this lesson. If you have further questions about the subject, you may call, text, send message via messenger to your subject teacher or advisor. See you again on the next episode for a new learning opportunities. This has been your teacher, Elena and Beduya from Pangan National High School. We heal as one, we learn as one through Bayanihans. Bongkaras Educat Balogan.
Ang ating radio and television-based instruction ay naisakatuparan dahil sa walang sawang pagsuporta ng ating City Mayor, Honorable Dexter Uy, ang ating Vice Mayor, Coefredo Tikwa Uy, at ng buong sangguniang panglungsod ng Catbalogan na pinangungunahan ni Councilor Honorable Step Uy Tan. Kaya, ang DepEd Catbalogan City Division ay taos-pusong nagpapasalamat sa malaking suporta ng City LGU sa ating mga mag-aaral. Muli, maraming salamat sa inyong walang sawang pagsuporta.
Kasanggamong Pilipino, anumang lahi mo. Kasanggamong Pilipino, anumang laban mo. Sa timog o silangan,